So hi everybody, Ekim Maurer. I work for IBM, former NS1, and I want to apologize that I do what big companies do all the time, cut down on the fun in this time your lunch. But I hope you can bear with me for a few minutes and listen to what I have to present. IBM was kind enough to pay DNS-OARC so I can play with the big boys. So I get a chance here to talk a bit about some things that we are investigating, trying to validate the hypothesis that we have. And this whole thing starts with actually what DNS is for us. Because DNS does its job damn well. And the job is resolve things, resolve IP addresses from names. For over 40 years it does it, and I've seen Paul here, so thank you, Paul. It's your fault. But everybody here in the room is living proof that DNS is critical. It is the one thing that is resilient across the internet, it's reliable, and it has a real impact. And we at NS1, or now IBM, always look at ways to solve things with DNS, because that's what we know. So I went to a lot of customers over the last 15 years now, and I talked to them around, like, what's your problems? What are the things you know, what are the things you don't know? And one thing in the last 4 or 5 years especially, I find mind-boggling. There was a big study done by Shopify and Amazon, and they found out that 100 milliseconds of latency on their e-commerce websites, 7% of revenue lost. It's not actually revenue lost, by the way. It's more or less money they couldn't make or would have made otherwise. But in Amazon's case, that's $4 billion a month. I wish I had that money there. But when I go to companies and talk to them about, hey, how much, sorry, microphones, bad. When I ask companies about, hey, what is your latency cost you? What's your problem with it? Everyone's, oh yeah, latency is a big issue. So can you put a number on it? And I get completely empty looks. Everybody's like, there's a cost? Yeah, I don't know. And I wanted to have a way to talk about that with them. So, as always, can I do something with DNS about it? Is DNS the one introducing latency? Or can we do anything with DNS to improve it? So what, with our limited abilities with DNS, what can we do? So I ran a little bit of an exercise. I'm lucky to have 2 ISPs at home. It's recorded, I can't name them. But one ISP is resolving things, no, sorry, let me start again there. I have a setup, I have a Raspberry Pi at home. I'm doing a normal lookup to a DNS service that I control on the public internet. They are completely under my control. There's nobody else using them. There's no load anything, recursive servers. So I cleared the cache everywhere. And I did a DNS lookup to Amazon.ca, I'm in Canada, to Amazon.ca, just to see how does it resolve. Are there things I need to look at? And my results were with my first ISP, using DNSSEC enabled and everything else. It took me 1.5 seconds to get the full resolution chain in DNS until I could get to Amazon.ca itself and load the page. Okay, cool. Let's clear the cache everywhere else again. And I did the same experiment with my other ISP. And I had half the time. Okay, failure in measurement happens. I repeated this test 50 times. The numbers were within 1%. ISP1 was constantly double the time for resolution than ISP2. The only difference is the ISP I'm using. It's the same Raspberry Pi, it's the same DNS service I'm connecting to. There's no magic in there. I was like, wait, yes, DNS is slow. I mean, this times, I don't like that, but why the hell are the results different between my 2 ISPs when every other thing is the same? So I talked to the smart people, and what's the bottleneck? Well, this was how engineers explained it to me. The data centers from Amazon, the DNS servers, the load balancers, everything else has a very good connection. So does my ISP usually. Both of my ISPs have good connections. But you know what? My neighborhood and the router that I use, they don't get that bandwidth. It's actually quite saturated. And then, yeah, inside my house, the network is better again. So traditional load balancers measure this, right? We know all of that. Edge load balancers, other systems measure the latencies, and those latency measurements allow us to do load balancing inside. That's great, but that's green to green. I don't think this is great for solving a latency problem. Third-party measurements are done on other networks, to the carrier side, to my ISP if I'm lucky, or to WAF providers that they have their own systems. And all of them end up having some measurements, but still they're mainly measuring latency between green or very high connectivity nodes. I need a way to measure it from my home, from my own system, from my own laptop. So how can I do that? RAM, or real user measurement. Actually, it was mentioned before in one of the questions, but we started to do beaconing for a while now, and we are looking at how does the connections work. So where do I go? It's quite simple if I'm staying across regions, like geofencing, geo-IPs is very established in DNS, ECS, thank you. But that was not the slide I wanted to go. So where we go? We get all these measurements, and that's all great. When I try to measure all of these things with our beacons, I'm using some advanced math. This exceeds me, so if anybody is interested, it's a great paper by Diane Lampert around the incremental quantile estimation of massive tracking. I have to read that. But it's basically a moving exponential average system that allows us to track very high numbers of data points coming in and make predictions out of them. It's a bit dry, but it's worth reading it. But what I see with those measurements after we calculate them is that if I'm going to, let's say AWS in this case, and I just picked AWS at random because I had the numbers from them, if I do geographical redundancy from my location, this is all measured from my ISP, my area, I'm getting back very predictive numbers for how long it takes to do a resolution and how long it takes me to actually download a little file from a system hosted on those, in this case, cloud vendors. This is great, and geofencing tells me the same thing. I mean, it makes sense. If I'm in Canada, in Toronto, which is the East Coast, it's easier to go to the US East than it goes to Southeast Asia. That is not surprising. But the problem is, a lot of people actually have nodes, multiple vendors, multiple clouds, multiple CDNs in the same physical region. How do I differentiate between the latency to go to AWS East versus Azure East? I can't do that with DNS today, really. DNS doesn't like geofencing, IP address don't give me that information as far as I know. And when I look at the latency numbers, they're quite close to each other. So what we saw is those numbers are close, but we need to find a way to move between A and B. So when we tried to do that, the first feedback we got was, this is not the job for DNS. Let load balancers, let WAFs handle it. Makes sense. Maybe it's not a job for DNS, but I don't like that answer. I never liked that answer. Because there are two options. You can either use in-band solutions. You are basically coming in, it connects to a system, and it forwards you to the same thing. But why did customers go to multiple CDNs or multiple clouds? They wanted to prevent a single point of failure. So we are solving that by putting a new single point of failure in front. Kind of doesn't make sense to me. You can use BGP and like the traditional way, oh yeah, let's use hop counts. Hop counts are definitely not good. And the problem actually with my latency when I did more measurements and more thing is that the hop count, both providers have a very good connection to AWS. The problem is BGP sends me to a bad node on one of the providers. It's shorter in BGP counts, but the connection is bad. If I go to a node that is 2 hops further, I have almost the equal connection times. What we have seen is if you don't want to be in band and you want to use a protocol that we have some control over, DNS actually is not a bad solution for this. It might be a job for DNS. But is it becomes the question. And the other thing, what does best mean? As I said, I'm from Canada. For me, best is Gretzky, nothing else matters. But for some people, performance matters. What's the fastest, lowest latency connection? How fast can I get there? Sometimes it's resilience. How available are the nodes? Sometimes it's simply cost. It costs me more to buy stuff from Amazon or AWS compared to Azure. Which one should I use? Those type of things are factors that we have to mix in. And how can we do that? Well, if we have a measurement of, these are the latencies, these are the performance metrics, this is the availability of them, and you customer put it in a calculator, that's the cost you have for connecting those. I can give you the best, and you define the specs. That was our idea, that was our hypothesis. But this sounds too easy. This sounds too easy. This is like, okay, great. World is great, but yes, we have to solve the last mile problem. We see problems already with areas that are less populated. It's very easy to get data from Charlotte City or from New York City from an ISP. I have hundreds and hundreds of users. But if I am in the middle of Vermont, where there are like 3 people with internet, it's really, really hard to get good measurements. So one of the questions, one of the things that runs through our engineers' head is how can we get better data from areas with less populations? And the other thing is, we are abusing DNS to do something. Are there any things that this usage of DNS, where we give like almost every 2 seconds different answers depending on who is asking, is that posing a problem for DNS overall? And we really want your feedback on this hypothesis. Does this even make sense? Or are we missing something majorly important on this? And guide us so we don't spend more time and can spend our engineers' valuable time on actually the things that matter, making DNS better for them. So with this, thank you for listening to me. And if you have some feedback, if you can help us, that will be highly appreciated.
Hi, Ben Schwartz, Meta. So you said something in the middle of your talk that made a lot of sense to me. You said that you did some deeper analysis of those 2 latency traces that you showed and found that Anycast was sending you to a poorly chosen location for one of your ISPs. So that seems like a very solid, correct analysis. But about 5 slides before that, you showed a diagram with a congested link, or maybe an underbuilt link, and you said that this was somehow connected to the problem. But if it's a BGP issue, that's all far upstream of your red links here. So could you help me understand what the connection is?
No, you're right. Those things are not necessarily correlated, but they play into each other. So if where is the congestion happening? There are 2 answers to that.
So I don't think there's any congestion in this story, right? It's just time of flight latency in 2 different uncongested networks. In
the particular use case that I used, yes, absolutely, you are right. Like that's something I made a bit of a leap there. We have also heard from our customers that the biggest problem they have is basically when they try to do streaming, especially, that the last mile connection is the biggest headache that they are seeing. That the congestion there, because people are doing 50 things at once. And when they are trying to download a lot of those packages, it becomes a problem. But there's sometimes nodes which have a better performance, even though you're congested, I can get the data a bit better from somewhere else. And if I incorporate that measurements for my ISP side, I see more. At the end, my finding with the bottlenecks in here did not necessarily result in the solution that we are doing. But I still think there is more that we need to look in there from bandwidth analysis. We have not gone that far, though.
Okay, thanks for clarifying the distinction there. I'll mention that there have been some research publications from Meta talking about some sort of large-scale dynamic traffic steering based on continuous analysis of congestion levels in edge networks. So if you're interested in that topic.
I've read them, I'm just not smart enough to understand them. So I'm believing in my engineers that they give me a TLDR on those things. I'm just a product manager, sorry.
Thank you.
And I hope this was not too bad for the first sponsored presentation. Thank you, everybody.